Hi everyone, we're going to solve this problem in the video, so if you want to pause it and take a second to try it yourself, that would be great. Reading the question, we are given some information. We have a mass of 5 grams of grapes initially at 20 degrees Celsius, and we're cooling them to a final temperature of negative 196 degrees Celsius with liquid nitrogen. And we want to know how much energy is transferred from the grapes, assuming that the grapes are 100% water. And then what mass of liquid nitrogen was vaporized in this cooling process. So again, as usual, I want you to kind of think of what's happening to each material as this process is taking place. So we have temperature versus heat lost for the grapes. So they're starting at 20 degrees Celsius, and they're going to cool to the freezing point, 0 degrees Celsius. They will freeze, temperature constant, and then it will cool again to negative 196. So we have 3 steps to calculate the heat lost by water. Then the liquid nitrogen is going to be gaining the heat. According to the first law of thermodynamics, energy is conserved. So we have this transfer of energy, heat energy, from the system to the surroundings. And since liquid nitrogen is boiling at negative 196 degrees Celsius, that vaporization phase will maintain constant temperature as heat is taken from those grapes. So we know Q system is equal to negative Q surroundings, or we could say Q gained is equal to the negative of the Q lost. And in this particular case, the grapes are losing the energy, so we can say Q of N2 is equal to negative Q of the grapes or the water. So I'm going to set this up where we look at QN2 separately from the Q water. So QN2 is equal to N delta H vaporization because we are at that point of a phase change, so we will use this formula. So how many moles of liquid nitrogen do we have? That's what we're ultimately going to end up solving for. We want to know what mass of liquid nitrogen is going to evaporate. And the delta H vaporization for liquid nitrogen is 5.59 kilojoules per mole. Okay, so we have that portion down. Then Q of H2O is equal to Q1 plus Q2 plus Q3 as indicated on the heat curve that I have drawn up above. So solving for Q1, we have a cooling phase, so this would be MCS delta T. We have 5 grams. The heat capacity for liquid water cooling is 4.18 joules per gram degrees Celsius. And my change in temperature, T final minus T initial, we have a final temperature of 0 minus 20 degrees, so we have a change of negative 20 degrees Celsius. And so this calculates out to negative 418 joules, and you'll see that it's going to be useful to put this in kilojoules eventually. So we have that. Then Q2 is my freezing phase, and we'll use the N delta H freezing. And delta H freezing isn't a number that we look up in the literature, but it's equal to the negative of delta H fusion or melting. So this would be the number of moles, so 5 grams divided by 18 grams per 1 mole. We have 0.278 moles of water, so 0.278 moles of water times negative 6.02 kilojoules per mole. I get negative 1.67 kilojoules of energy to freeze, to freeze that ice in the grapes. Then Q3 is cooling from 0 to negative 196 degrees Celsius. The heat capacity for ice is different. Sorry, I have to scroll back up here. 2.09 joules per gram degrees Celsius. And delta T here is going to be a negative 196 degree temperature change because T final minus T initial, we have negative 196 minus 0 is negative 196. So this calculates to 2,048 joules, which is 2.048 kilojoules. So I add all this up. Q1 water is equal to minus, sorry, this should be negative as well, minus 0.418 kilojoules, minus 1.67 kilojoules, minus 2.048 kilojoules. So this is minus 4.1314 if we round kilojoules. All right, so then I know that Q water, Q8N2 is equal to negative Q water. So QN2 is N times 5.59 kilojoules per mole, equal to the negative of negative 4.14 kilojoules. So I will end up with N equals 4.14 kilojoules divided by 5.59 kilojoules per mole. My final units are moles. I get 0.7399 moles. And then to convert moles to grams, I multiply by the molecular weight of nitrogen. Nitrogen is a diatomic, N2, so the mass will be 28 grams per mole. And the mass that I will evaporate here is 20.7 grams. Okay, so the key feature here was knowing this QN2 is equal to negative QH2O, the idea of the first law of thermodynamics, where heat is conserved and transferred from one thing to another. Thanks for watching.